we propose DPCS, a path tracing-based differentiable projector camera systems. Start from the topic about projection mapping, PM. Projection mapping is a well-established technique which aims to augment the scene or control the appearance of the scene using the projectors. While this technique usually needs to simulate the project and capture process of the projector camera systems, ProCams. More specifically, it involves calibrating or estimating the geometric and photometric properties of the ProCams. After finding both photometric and geometric mappings of ProCams, projection mapping techniques can be applied to augment the scene. A few research papers have already tried to simulate such project and capture process. The most straightforward solution is to per pixel simulate the ProCams. This usually involves first calibrating or estimating the pixel correspondences between the projected pattern and the camera-captured image. Then, using this correspondence, warp the projector's perspective to align with the camera's front of view. Next, fit a nonlinear function, f, which embodies the luminance transformation between corresponding pixels, basically accounting for how brightness changes in a nonlinear way from the warped projector input patterns to the real camera-captured images. This function f may include projector response function, material properties, exposure, and so on. Finally, by applying this nonlinear function to the warped projector input image, we can simulate the scene as the camera would really capture it. Another line of work trains an end-to-end neural network using pairs of projector input images and camera-captured images to simulate the project and capture process. After training the model supervised by the projector and camera-captured image pairs, we can inference on the novel projector's input images. With the well-trained network, we then obtain a simulated camera-captured image. This approach implicitly learns both geometric and photometric properties in the network parameters. Unlike per pixel simulation, global illumination effects between different pixels might also be implicitly learned in neural network parameters. In summary, current methods often face the following challenges. For per pixel simulation approaches, they typically require fitting a nonlinear brightness transformation function at the pixel level between projector and camera-captured image pairs. Such an approach might not fully account for global illumination between different pixels. Moreover, since the nonlinear function used to fit the brightness transformation essentially encapsulates nearly all photometric properties, it becomes challenging to edit parts of the scene to virtually test projection mapping effects. For instance, change the scene's material or geometry. What would the scene look like? On the other hand, for neural network-based simulation methods, using a neural network to implicitly learn the projector's indirect light may be inaccurate, especially for complex projection effects like interreflections. Additionally, relying on neural network parameters to implicitly represent scene parameters may lead to suboptimal results when trying to edit them. Next, let's briefly review our solution: path tracing-based project and capture simulation. Assume that the scene contains only one projector acting as the light source. Instead of per pixel or neural network-based simulation, we can express the radiance at any point in the scene, whether emitted directly by the projector or reflected off surfaces, using the rendering equation. And here the direct illumination refers to the radiance captured by the camera after only one bounce. Indirect illumination is the radiance that reaches the camera after multiple bounces within the scene. Then, any radiance that reaches the camera's sensor lens is captured to form the irradiance. Finally, the camera's exposure, response function, and related processes convert this irradiance into the final sRGB image. The second row in the figure below visualizes the contributions of both direct and indirect illumination to simulated camera-captured image. And the real projector and camera-captured image pairs of the scene shown in the first row. Note that the rendering result for indirect illumination has been exaggerated for better visualization. After formulating the path tracing-based problem, we can estimate the scene parameters using a differentiable renderer. First, we calibrate the projector camera system and use gray code structured light to capture the scene's point cloud, which is then converted into a mesh via Poisson surface reconstruction. Next, the calibrated geometry is fed into the differentiable renderer, and a forward differentiable rendering pipeline simulates the light transport of the ProCams using predefined scene parameters, such as surface reflectance, the projector response function, and the camera response function. This forward rendering approach produces simulated camera-captured images under different projector input patterns. Then this setup can be leveraged in a gradient-based optimization to minimize the pixel loss between the denoised rendered images and the real camera-captured images by differentiating with respect to scene parameters theta. Once we use this analysis by synthesis optimization described above to estimate and obtain the optimal scene parameters theta hat, and we end up with a virtually trained ProCam setup. Since many parameters in the scene are differentiable and editable, we can apply various applications. For example, with ProCam's relighting, we can change the projector's input to IP star in the trained scene and then obtain a simulated relighting result for a novel projector input pattern onto the scene. It enables the design, testing, and debugging of novel light patterns in a virtual scene before actual projection. We can also perform projector compensation. Given a target appearance, we differentiate with respect to the projector's input so that the forward rendered image matches the target effect, thereby enhancing the user experience. Additionally, because some parameters are editable, we can modify the scene parameters in this virtually trained ProCams setup to simulate how the projection mapping effect would look when new materials are introduced into the scene. The figure on the right shows material editing for two scenes arranged in two rows. The first column displays the scene as captured by the camera. The second column shows the relighting result obtained by changing the projector input pattern. And the third column presents a novel scene rendered by the camera after the PBR material of the scene has been changed while projecting the same pattern as the second column. Similarly, the geometry of the scene can also be edited. Here we demonstrate an example where our DPCS applied to compensate for a morphing surface. We show the ProCams relighting comparison between the proposed DPCS, a pixel-wise method TPS plus SL, neural network-based methods ComponSD++, and the ProCams. In the first row, we show the projector input images, the scene, and the camera-captured images as ground truth. In the bottom row, we have different method-inferred relighting results. Clearly, our DPCS outperforms better quality, especially for the indirect illumination area, where we presented with zoom-in patches. We also show a comparison for projector compensation. In the first row, we show the projection surface, the uncompensated result, and the desired effects. In the bottom row, we have real camera-captured compensation from different methods. Our DPCS performs similarly to ComponSD++ and outperforms the other two methods. Finally, we'll discuss the current limitations of DPCS. The first challenge is DPCS relies on calibrated geometry. Performing mesh optimization on real data often involves challenges, such as handling discontinuous gradients, as well as mesh regularization, topology changes, and subdivision. The second challenge is ambiguous BRDF decomposition. The different BRDF maps estimated by DPCS tend to be coupled. Incorporating extra supervision from multiple viewpoints, such as specular highlights seen from different angles, might help constrain these BRDF maps. And the third challenge is real-time applications. Since DPCS requires full light transport simulation of the scene, it often needs to find a balance between rendering quality and real-time performance. That's all. Thank you.